Thank you very much for the kind welcome and the introduction, the invitation. It's a great pleasure to be here and also quite an honor that you decided to spend your lunch break with me. I have a first introductory slide, which is a brief history of materials, because I want to talk about materials that make robots smart. And so, you know this, you have seen this before. There's the Stone Age and then the Bronze Age, and maybe you were a king and you had a big army that had bronze swords, but then the next day somebody came with a steel sword because they added some coal to the fire when they smelted it, and then your little civilization was gone and the Iron Age civilizations came in. And I think the pinnacle of the Iron Age was the steam engine. I made that up. I'm not really sure whether there's agreement in the room. But then the plastic age came. And so I think the observation here, it's not only about war, but it's also about economical growth. So the steam engine was the last internet. If you think about what happened in America, 1800, or Leland Stanford, I think he was a railroad person. And so now we have that plastic age, and the pinnacle of the plastic age are the products that you guys are developing and selling. And so the biggest companies in the world, the most valuable companies in the world, are now selling highly integrated electronic products. I put the turbine in the middle here because the jet turbine is now made from composite materials, which is a big thing in the plastic age. And I found it interesting that people were thinking about composites for quite some time, but then it took Rolls-Royce to actually put it into a flying engine, and that was really where the field took off. And since the 60s, composite materials is a big field. Now, the other observation that I want to have you make here is that things go really quickly. So this is an exponential thing. 300,000 years, people were clubbing each other with these flints, and then very quickly they developed. And so the question is, what's happening next? And is there anybody who wants to volunteer? Maybe you thought about that too. What do you think is going to be next after the plastic age? Yeah, so silicon will probably carry forward, but I think the plastic age encompasses this. And so other people mentioned carbon, and graphene and things like this, which will revolutionize. And I think these are the tools we will need for the new age. And I think the new age will look like a little bit like this. I was promised sushi today, and I thought you all have little octopuses in front of you, but not everyone brought some. So this octopus is trapped in the jar and can free itself from it. And I'm fascinated by the octopus animal because it has this massive integration of sensing and actuation and computation and communication. So it is a material that is soft, yet has this high integration. And I think the Samsung watch or like a cell phone is already very highly integrated. You almost have no things left in it that are just monolithic or homogeneous materials, like the plastic casing. Almost everything in it is highly integrated stuff, much like this octopus. But yet there's a new layer of complexity that I think we should look at as engineers. And so, in particular, the octopus has 2/3 of its neurons in the arms. So you have all of your neurons in your brain. The octopus has distributed that intelligence. And so now uses, I don't know how that works, but it kind of figures it out and then escapes the thing. So closer look at these kind of materials. I have a slide that was a science paper in 2015 where we reviewed all these possibilities. And what you see are different natural materials that all have those properties of very highly integrated sensing and actuation next to each other. So the cuttlefish, for example, has these chromatophores which allows it to change color rather quickly. The skin is fascinating. It has 4 tactile sensors. It has a vascular system. It has a nervous system. It has actuators. It can sweat. It has hairs that it can erect. And so I think if you think about making such things, you have tremendous opportunities in the engineering systems. So camouflage or shape-changing airplane wings, bridges that self-repair and self-diagnose. And I have the bone in the top. I think the bone is very interesting because everybody who studied material science already knows how great the bone is, and people go on, and maybe you even find somebody who tells you you have to design your cases like a bone so they're lightweight and still stiff. But actually the bone is much more complicated than this. It has nerves inside, it can store energy in terms of fat, it generates white blood cells, and it is essentially an automated system. It's like a living machine. And so what I envision is to go to Home Depot, and you can buy 4x2s, but you could also buy 4x2s which have bone properties. They're a little more expensive, maybe 20% more, but then you get that features. Or like living wood. So wood is something, lots of things in here are made from wood, and actually all composites, highly engineered composite wood materials. But people don't even think about what would it take to make something that is like living wood. So I can sell it, and then it alerts me when it breaks, it repairs itself, and so on. So in this talk, I want to describe in more detail 3 biological systems that I find fascinating and that we try to re-engineer in our lab. And I apologize right away because everything I do in my lab is very clumsy. So you see these clumsy things there because we make it with our hands, and we have like 5 to 10 students working on this kind of stuff. And we cobble it together in some funny way. But I think that nothing here couldn't be made as integrated as the biological systems if people decide that it's ready to transfer. So the first thing is the octopus arm. And here you see how it looks like in a medical drawing. It has something called muscular hydrostats, which are muscles which preserve their volume but can change their shape. And so what you can do with such a thing is you can work them antagonistically, and that makes the arm stiff. Or you work them complementary, that allows you to bend. So the octopus can choose between whether it is a skeleton or a muscle. So everything in the arm can become skeleton or muscle alike. And then there are these 2/3 of the neurons in the middle which actually do the control. So we tried to build something like this. There you see the octopus or the cuttlefish chromatophore, which has a pigment bag in the middle. And then there's an annular muscle which can open and close to display this to the outside world. But you would find like hundreds of papers where people say, oh, we solve camouflage. But what they actually do is they try to make a way to display color. And so even OLED people claim they do camouflage. Try to put on an OLED on a soldier. Everybody can see the soldier, of course, so it's not how it works. It's some kind of passive effect that you want. But not only that, you also want to have a nervous system with it, because all these chromatophores are connected to the brain and with each other in really complicated ways that we don't understand yet. There's computation happening, there's communication happening locally, and we try to mimic this. And finally, the skin is very fascinating. I mentioned the 4 different tactile sensors, the vascular systems and all of this, and we have 2 applications there. So I want to walk you through those 3, and then want to reconnect with possible applications that we can do now, and discuss with you of whether this is actually a new material age or whether this is just my own funny dream. Okay, so the first one is this octopus arm, and what we've done is we built a shape-changing composite, and you see here these things are thermoplastic, which melts at 60 degrees Celsius. So we took the thermoplastic and we wrapped it around nichrome wires, which can heat it, and we added a little thermistor so we can control the temperature of it. And when you melt it, it becomes very soft, and when it's cold, it's very stiff. And we encased it into rubber, so we have actuator that can change its stiffness. Then each of these actuator pairs has a little computer that controls the temperature to a desired set level. Now the idea is to have a beam made of these things, which you see here. And let's say I want to get the beam in a certain shape. I can then calculate the stiffness that I need, then apply some moment so the beam will bend. And then I freeze it, and I think about bending it the other way, and I get any shape I want. So I hope that makes sense. I can tune the stiffness to certain computed levels and then get that thing in any shape I want, and then it's stiff. So I could make like a surface of a car to, you know, aerodynamic profile. I could make a spine for a robot or things like this. Now we upgraded the design a little bit over 4 years, and we came up with something like this. So again, same thing, but now we have this spine-like structure that we encoded in rubber. And we are very well able to predict how much stiffness we get or how long it takes to heat it to a certain temperature. And then we are able to bend it into different shapes as a function of the temperature. So you see here, if it's very hot, 10 Newton of force will bend it more than if it's colder. So the interesting thing computationally here is, I think, to solve the computation. And so the octopus community is fascinated by this and says the robotic people need to have, it has 100 degrees of freedom or something, and they have all this complicated math. So where is this octopus doing that math? And we don't know, but we came up with an algorithm. So just technically, if you have 100 degrees of freedom, you need in the order of 10,000 operations. So it's an order of n square complexity that you have to solve. And here I make fun of my own community. The computer science people came up with a distributed algorithm that would go in order of log n time. It only requires n to the power 4 computers. So if you have n to the power 4 computers, you can solve it much faster. Doesn't work, of course, because I have only a linear amount of computers when I build an ARM like this. And so now our algorithm is as follows. The problem is you have something which has, this pointer doesn't really work, but here it is. So you have a couple of degrees of freedom here, and you want to get this point to that point. So how do you do that? That's the question, and this is the order of n problem. And so the way we solve it is we say, we fix everything but 3. And now the problem is an order of 3 square problem. I'm only allowed to change these 3 things to bring this as close as possible. So I do that, and then I move on and shift the 3 that are allowed to do that. The pointer doesn't really work, so I will not use it. And so then I use those 3, move a little more, then move on. And so what I kind of get is some kind of computation that travels through the arm from left to right. And so each time I try to solve the local problem. Let's move a little bit, let's move just here so that I get from here to there or something. So I move, this is a good way. So then I say, okay, now I can move here. So I move that, and so on. And so this is an iterative process which basically runs through that material and computes, and then the thing converges. Now, the octopus people have studied the neural activation. I wrote a paper in soft robotics. I said, please, the famous octopus guy should review it. I don't know what he thinks yet, but maybe he will not understand. Let's say it's rubbish. I don't care, because we can make a material now that you can, if you want, I mean, if you would want, buy at Home Depot, which would solve that problem, and it doesn't matter how long it is. So here's how it looks like. We want to go from the start is the blue, and then the goal is the yellow line. And then we have our system here. We have all these computers. They calculate things. Then we set the stiffness, and that thing snaps into place. So this is the first example of distributed computation and control. The next problem we studied is camouflage. So camouflage, you know, I show these pictures that you all know, but the point I want to make is that there are only so many patterns in these camouflage scenarios. There's usually this vertical stripes and the horizontal stripes and models and combinations thereof. So the cuttlefish, the chameleon, see, it shows the same kind of patterns. And mathematicians, actually Alan Turing has come up with the equations you see in the middle in 1952, which is a partial differential equation, which when you solve it generates those kind of patterns. And as a function of the different parameters you can set, you get those stripes and models and things. So what we have done is we made a bunch of smart, oh, thank you. I do actually have sound later, that would be great, so good that you have control. Thanks, Catherine. We made a bunch of smart particles, which are little robots that can talk to each other with infrared. So they have 6-channel infrared, and they can sense color and they can change their color. And now I want to do camouflage by putting them into rubber. And now you might say, well, this is too clumsy, this will never work. What we try to do here is to say, I build it, and I want to know what are the computational requirements, and then I find someone else who can make it as small as possible. And I have friends who make it like 2 by 2 millimeters now. You can make 2 by 2 millimeters, and it's really painful to do that. So we're not going to do it. We are studying the algorithms and demonstrate, and we're also looking for people who can do passive coloration change. And this is something you could do with e-ink or something. But so this is the system. Now we have a couple of distributed algorithms. The first one is we want to find out the colors that are of importance. And so the way we do that is we just we bin the colors that we see into 8 bins, or some small number, and then have the swarm consensus on it. And this is a typical swarming algorithm. It's called consensus, which is essentially averaging among your neighbors. So I average among all my neighbors, they average among all their neighbors, and eventually this converges to what the consensus is. And in this case, they consensus not on a single value, but on the bin values of these. And I would argue that if you take the first 2 or 3 most dominant colors, you are on a good track to make sensible camouflage. So here you see there are browns and there are greens and there are yellows that dominate. The second algorithm is to find out whether the swarm is in a vertical stripe environment or horizontal stripe environment or in some kind of modeled one. And the way that works is I can just calculate the gradients, the local gradients, by talking to my neighbors. And what you do is you do a convolution with a Laplacian filter, but it is unnecessary explanation. It's actually a Sobel filter that the system runs in a distributed way. And then we can say, how many vertical edges do we see? How many horizontal edges do we see? And then look at that. And if one number is higher than the other, I'm in one of those environments. If both are approximately the same, I'm in this modeled one. Finally, we need to do pattern formation, and there's something called Young's algorithm. And here it would be good to have the pointer again, can resuscitate it. So here the idea is if you have one particle that sits in the middle, and it can see the values of all the particles in these shapes, then the decision of whether this particle is on or off depends on how many of the other particles are on in the orange area and how many of the particles are off in this area. So what will happen is that if you run this and you keep running this, if you use these kind of shapes, the left ones, you will get horizontal stripes emerging. If you do it in the middle one, you will get vertical stripes emerging. And if you do the right shape, you will get those model patterns. And so these things that I showed earlier are simulation results where we actually don't solve the partial differential equations, but this simplified algorithm. Now I can run this on the real system. And so what we've done, we deployed these little robots, so 8 by 8 little robots. They are only communicating locally. And I start running that algorithm, and then you see in the middle how they converge to the different patterns and then self-organize to create patterns like this. So what I'm really eager now is to find people who want to make it small, and eventually maybe we can have just smart paint, which you mix into a liquid, and you paint it on, and you get that kind of camouflage behavior. There's no physical limitation, no computational limitation. It's more like whether you want to do it or not. Wireless powering is a problem, but also that is not as difficult. All right, so the next biological system that I want to focus on is the skin. And we have been, at first, been fascinated by the Pacinian corpuscle, which is responsible for your texture sensing ability. And when you rub different things, it sounds differently. You can actually use the microphone, and I could rub it on the floor and on different things, and you would hear different noises. And that's what we do in the skin, but that's also what we build. And what we place the microphone inside of rubber, and then we measure some kind of signal, and then perform a fast Fourier transform, which essentially bins the frequency component and counts them in a histogram, and calculate an ambient and a transient signal. Now, once we have that, we can do interesting things. We can look at the power spectrum of it. And so what you see here is 3 different sensors that measure the power of what has been recorded in the middle of them. And not surprisingly, it fits this 1 over R expectation that we have. So sound attenuates in 1 over R in a medium like this. So we can calculate where it came from, but we can also go and classify it. And for that, we had 15 different textures that we rubbed over the material. And so here you see it's Brillo and sponge and finger, and also actually I've written here fine wire mesh. So we have 15 different of these. And you see the spectrum is completely different as a function of what it is. And so with a simple classifier, simple linear regression, which is like around 2,000 bytes worth of weights, we can implement that on a very small microcontroller and tell you what touched it with like around 70% accuracy. And now the accuracy is very low. You can actually bring this up to 99%. But what I wanted to point out is that we can create a material that you could theoretically buy as a skin and cut it in any shape you want, and it will always work and it will do its thing independently of any other computer. And so here the student rubs it, and when he rubs it, you see in MATLAB where the nodes have estimated where it happened, and then the data of the classification I showed you earlier. Now you can also take the same technology and drop it into a tire. So we're an RC car, and we have a little tire which has piezo microphones inside. And now you can drive over 8 different terrains and tell what the terrain is with 99.9% probability. And now in our science community, we fight with the other people. And so this is a little better than anything else out there. People put microphones next to the tire. But it is actually much faster. So nobody can tell the ground as fast as we can. And I have a fantastic pun because we put the sensors where the rubber hits the road. So you see here now in the video where the car drives, and blue is concrete, then it switches to grass when it's on grass, and then it can go into the gravel, and you will see it recognizes that. And so we're currently trying to actually make maneuvers with the car that are using this information to make very robust behaviors. Okay, so more on tactile sensing. The skin has not only the perceiving corpuscle, but has 3 more sensors. And so we wanted to have those for robotic applications. And what we came up with is we take a cell phone, the sensor in the cell phone that tells you whether you have the phone at your ear or not, which is a proximity sensor. It's really cheap because people sell billions of these cell phones. And we put it into soft rubber, so you see that in the bottom. And when you do that, you can still see objects that are outside of the robot, but then you can also measure contact with the surface, and you can measure pressure. And so now the rubber behaves like a spring. When you start deflecting it, I can measure the force. And so to the right, you see how I first measure distance up to 5-6 centimeters, and then to the left, we are measuring the force. And the most interesting thing is the thing that happens at contact, which is 0 force and 0 contact. 0 force and 0 distance. And you see that here there's an inflection point, so I can very exactly tell when I make contact with an object. I will show you that in a second. So here we did experiments and had robots grasp things, and I learned that grasping is not just I grasp or I don't grasp, but it's really a sequence of many actions. I think it's more complicated in autonomous driving to grasp things and manipulate things because so many things are going on, and you don't really see that, you don't think about that. But here, you approach an object, and then you align yourself with the object, and then you make contact, and then there's a loading phase. There might be different disturbances, and then when I replace, I have a new state where I actually think about, okay, slowly, so I make contact with the table, and then there are many things that are going on until I do release. And now if you look at the sensor signals that we can get from that simple sensor I showed you, when you have contact, I get a really big peak, and when I have a release, I get the peak in the different direction, which is the third bar, the FA1 channel we call it. I can see the disturbances, and I can measure the pressure during grasping. So we try to use that to build a tower, and we used a really bad robot, I will not blame the robot maker now, but it's a bad robot, and it's very hard to make a tower of even 2 levels high. And so what we've done is we've done it many times and measured the percentage of completion rate. And so without our sensors, we couldn't, with the algorithm that we chose, and maybe we could have done it better, but the way we did it, we could only do make it 2 level high. Now oh yeah, when it's disabled, we can only make 20% success rate for 2 level high towers, and we could never build a tower from 3 pieces. We just couldn't, because the robot would knock it over, and it doesn't find the blocks, and there's all sorts of failure modes. Now we add the sensors, and I illustrate that here so we can see where the tower is, we can see where the blocks are, and we can help with the coordination, and we are much more successful in making 2 level high towers, and are now able to even make higher towers. Now this is not an industrial robot which could make towers as high as you want. This is an autonomous robot that has very poor sensing and very poor control, so it's a very constrained environment. I have another video here where, oh, am I allowed to play this? Apparently not. Yeah, if I click, I can only move. Does that play? No. Yeah, I do. It doesn't. Yeah, I hope the other videos work, otherwise we will. This one is not so important, so what we do is the student places these little wooden blocks in some kind of random configuration, and now the robot goes along and actually finds them using these built-in proximity sensors and grasps them. Now we were really excited about this and started commercializing that, and this video I want to play because it's nicer and it has sound. Is that allowed to play? Here. So if you want to crank up the sound. Oh, actually I can narrate it. So what we've done is we put the sensor on a commercial gripper. It's the robotic gripper, and on the universal robot arm. And we fully integrated it with their pendant programming software. So now you can just take that sensor, put it on, it takes 15 minutes, and then you can use the sensor information. And here we have a demo that I think will hopefully get clicks, because people like, actually if you really want this, then just buy 2 dishwashers, one for the dirty and one for the, but that's another story. So now what the sensors do is, I can now operate this robot without using any other sensors than these in-finger sensors. And I should probably rewind this because I carried away with my ranting about the dishwasher application. Yeah, it's weird because I can't see when it plays or if it does or not. Does it? Okay. So what happens here is, let's say you know the dishwasher because it's, you can download from the internet where the plates should be, and you have a robot that drives up to it. So then you might register the robot with the dishwasher, and so you know where you have to look, but you don't know where the plates are and whether they are there. And if you look carefully, you will see that the robot does some maneuvers in order to actually grasp those plates. It knows where they are, then it pushes one away and grasps it. And now what we show here is the robot scans, and whenever there's a plate, there's a big peak in that sensor signal. So I argue that this is actually sufficient to solve that task. So to just have those sensors and don't have a vision or like a 3D perception system. And of course, you want to combine those, and what this shows is a 3D perception picture that is very coarse, where then the robot goes and touches to get the full picture. Okay, so I want to get back to our discussion. Is this a new material age, or did I just make this up? And the answer is I'm making it up for 8 years now, and I started believing it. So I think we can talk about everything you've seen today as a material, because you do have regular patterns of sensing, computation, actuation, and communication. And so you might not be ready to accept it as a material because you can still see the constituents. So you see the rubber skin and you see where the computers are, but that's not a problem. I can make that smaller. I just have to have like flexible electronics or polymer electronics or something, and you can stretch the electronics and you get what you want. And then you don't see it anymore. So the next thing is there's emphasis on local communication. So I never communicate with anything else than my local neighbors. So the in theory, or actually in practice, I can cut this in any shape I want, and it always works. Because there's no notion of central, ownership or something, or control. The individual hardware requirements are minimal. I'm using very simple microcontrollers. And now you can buy, you have an Internet of Things platform, which you show in your center here, which I think is like 1 by 1 centimeter around. So the chip inside is probably 6 by 6 millimeters. So you get like full internet, like full TCP IP stack on this small footprint. So I think anything goes in terms of size. We demonstrated complex pattern formation and pattern recognition. And so when I say pattern formation, I mean getting something into a shape, displaying camouflage patterns. When I say pattern recognition, I mean something like detecting the environment you're in, or detecting, touch patterns. And the interesting thing here is that you don't need to know how that works. You just buy a piece of beam from Home Depot, and it can change its shape. Or you buy skin, and you put it on your robot, and the robot knows what's going on around it. So it's really a material because you can abstract it to stuff like skin, or the tire is just smart rubber. If I get to the point where I can mix this into the rubber, and I think there's not a big problem to do that, I just have to have small computers that maybe have piezo power generation, and they can talk wirelessly, and so when the car starts moving, they get powered up, they sense the vibrations, talk to each other, and send out where they think the car is driving on. Then I really have smart rubber. So what is needed? I think we need to, the stuff that you've seen, I would love to see to be better integrated. So I'd like to see demonstrators that are actually impressing the everyman who needs to see this, or who needs to see the technology being completely hidden. And I think this is something industry needs to do. It's not gonna be me. And I tried myself at this robotic materials company where we sell these highly integrated sensors. But I think there's more potential, the other applications I showed. I think we need to show more new capabilities, because if you can just do things that you can already do, people are not really interested. So it has to be something revolutionary. And a coffee cup that keeps stuff warm, it's just not exciting enough. So we're still looking for applications. So I think the camouflage is interesting, the shape change is interesting, the skins are interesting. We will need more and better manufacturing techniques. If you make these things yourself, you see that they are not really, I use like Chinese contract manufacturers for the PCBs, but there's still this putting together part. And so I am envisioning some kind of robotic assembly which uses many different, capabilities like 3D printing, PCB assembly, and composite layup technologies that are all coming together. And I think industry is moving there with this lasers direct structuring that is used to make antennas and cell phone cases. So there are things that the industry already does which you could leverage. And finally, I think we need to do some more research, and I try to gloss over it and say during my talk, everything is already done. No, it's not. We need better ways to provide power. We need wireless powering, I think. And so then the idea is you have a skin that operates by wireless power, but inside the robot there is something that provides that, or you harvest it from the 2.4 gigahertz network. And you need better ways of integrating. I mean, I write here vascular system because I think that's what people do. That's what most biological systems do. And I write nervous system because, and so here I envision really this idea of having smart pellets that you put into any polymer, and there's some kind of vascular system that powers them in some way, and then you start making robots like I described. So. The approach that I'm choosing is in order to pull this off, because you might think, well, this is all neat and cute, but now what's going to happen with it? And so I'll tell you what I now got done in the last 8 years pushing this is the first thing that I do is I evangelize this new class of materials like I do today, but we also have workshops. And the next workshop is going to be in Washington, D.C. in the Keck Center of the National Academies. And I raised money from the Computing Research Association to invite 25 government scientists, or actually money, also legislative people, and scientists, and the last one was in Boulder, so we got people from all over the world to come and discuss that. And then we publish it in high-impact journals, so in Science and Science Robotics, and the premier robotics workshops and conferences. Then the second thing is we started a center at CU, which has 35 plus faculty, which are arranged around the theme of multifunctional materials. And there we have an advisory board, which you are welcome to join if you're interested and engage. And it really is polymer chemists at the very bottom of this hierarchy of materials and application people. So we have a lady who does spacesuits, which are essentially robots, or I would call them RVs in space that you can wear. They have a restroom inside, everything. They do compression, they need a lot of sensing. So these are the kind of material or applications that drive the materials we want to develop. And yeah, I think that's what is to say about this. And finally, I try to demonstrate commercial viability with this company. Because if you don't do it, I have to do it myself and keep pushing that until we see this transformation happening on materials that are tightly integrating all these things you've seen. So with that, I would be happy if you have some questions, and maybe we can have a discussion about whether this is a material revolution or not. Thank you very much.
If you had to talk about like things which come out on the market, which will be commercial in the near future, what are some examples you can think of?
I think we already see a lot of these things. Wearables we see composites. But what I think is going to be big is robotics. There will be skins for robots. There will be sensors for robots. And I think it's really the autonomous systems that drive that kind of stuff. So if you have an autonomous car or an autonomous robot, it will want to know when it breaks. And things like that. So you will see much more of self-diagnosing and composites which integrate non-destructive evaluation techniques. The aerospace people developed this for years, but the aerospace people are very, very conservative. They would never fly anything like this, which adds weight and cost. But I think it's going to be autonomous cars that will have surfaces of that kind. And eventually, I think the high integration of things that you see in this cell phones and the watches will just become everywhere. So you will have like maybe dinnerware that has like computing inside, or like furniture and things like that.
Hello. Hi, my name is Alessandro Zago. I have a question. So obviously you are at the forefront in this field, but can you name also other top 3 centers in the world that are, working complementary or in this field and you think are some of the top?
Yeah,
today?
so I invite them to these workshops. And so George Whitesides is definitely pioneer in the soft robotics space, and also in lab on a chip and all sorts of enabling technologies, who thinks about systems like that. There's John Rogers in Northwestern University who does stretchable electronics, and they are mostly focusing right now on biomedical personal medicine applications. Then there's non-destructive evaluation is Fuku Shang in Stanford, who does airplane wings. And I bother him. I mean, from him I learned that. So they're also in the picture. If you look carefully, then Fuku will be there or something. But he now also does cars and batteries, composites with integrated batteries. And so then there's Daniela Roos in MIT. So there are lots of people who are doing these kind of things. I think I'm the most crazy person from them by pushing. I come from swarm robotics, and I'm fascinated by how atoms, or your body is made of atoms, and how they interact to make a smart something. And so that's what I'm pushing with these materials. Thanks.
I have a question about your tactile sensing. How well does the tactile sensing approach human levels of sensitivity and the speed with which we can respond to changes?
Yeah, it's an interesting question. It is much better in many ways, and it's much worse in other ways. And in general, robotic manipulation is very, very far away from human level performance. I think it is much better in the way as that it provides proximity. And so if you can see something before you actually touch it, you have a lot of extra opportunities. And so I think these kind of sensors will eventually make performance superhuman. Like wireless communication also exceeds any natural communication ability. So on the other hand, we are still far away from like language and things like that. So it's always, it's difficult to compare.
Yeah, so between, I think there's three main components: is sensing, compute, and material. Like these are that give rise to this, like, let's say, smart material. Would you say that of these three, anyone dominates in terms of the bottleneck of what needs to happen to enable this? Or is it pretty
Dominates in terms of applications, or
no, in terms of the remaining work need to be done to make this more viable? Because you said there's remaining research work and also commercialization work.
So actuation is the hardest because it requires power.
Okay.
And a lot of power, and you can't bring the power in. And so I focus mostly on actuation in terms of turning a light on and off. I mean, I have this moving thing, but it's really difficult. And I feel like we get a lot of mileage out of high bandwidth processing locally. So the Pacinian corpuscle is sampled at, in your body has resonance frequency at 250 hertz.
Mm-hmm.
So if you have thousands of those on a smart surface like this, how are you gonna route all this information, process it? No, you don't. What you do is you put little pin-size microcontrollers next to it that do that. And so that's what I think where I have the most success in doing distributed local computation on sensing, high bandwidth sensing.
Okay. And a follow-up question then is, in the computation, I mean, this is taking distributed computing to the extreme, right? You want like many, many very, very small compute nodes. Do you think that there's a need for new architectures to facilitate that, or you're happy with the current state of microcontrollers and things like that?
Yeah, so I wrote a position paper with Chris Pistel. He was at Berkeley here and is the smart dust guy. And
Yes.
so Chris and I organize also the workshops with a chemist from Cornell, Rob Shepard. So that's the team.
Mm-hmm.
Wireless sensing guy, chemist guy, and robotics person. And we brainstormed about this a lot, and he thinks silicon is actually there. So you can have thousands of these things talk to each other. And we can probably, right now I play a lot with this Internet of Things, and I don't have a problem with an airplane wing having 2,000 IP addresses. And of course, then you have a channel allocation problem, and you need to solve that somehow, but there's so much algorithms already out there that we need to unearth from the sensor networks community. So it's not completely clear to me. I think it's really about making large-scale wireless systems.
Yeah.
And then the architecture changes might actually come from the power requirements.
Yeah.
Because like Chris and his people, they already have wireless power, but it will affect how often you can do certain things and how you do them. And so I think we have, that's not the problem right now though.
Okay, great, thank you.
Thank you, Rashid.
Thank you, Nikolaus. And I think we got to the end of the questions. And I just wanted to say thank you for the talk, and
Well, thank you very much for having me.
giving a gift from Samsung,
Oh, thank you.
which has a lot of storage, and you hopefully don't have to recycle it very soon.
Thank you very much. Danke dir.